Alright, hey guys. Today the plan is to do Code Jam, round 2. And yeah, I'm a bit late because I was trying to fix my audio again, because I had tested it the day before, and then it was fine. And then that was yesterday. And then today, apparently the action of turning my computer off and on again messed with the audio or something, and so it was quiet again, even though it wasn't. So I just unplugged and replugged in my microphone, and apparently that fixed it or something. So I have no idea what that is, but hopefully it's good now. I think I've been trying to fix it since last time, since I know it was messed up before. But yeah. Okay. Whatever. Let's just do this. In this problem, you need to sort distinct integers in strictly increasing order. You can rearrange the list by swapping the contents of any two positions. The minimum query gives you the position of the minimum value. Are all elements distinct? Yes, they are. Okay. Minimum of the range. So it's 10 to the 8th divided by the length, and it likes smaller lengths? Okay. So 6 times 10 to the 8th. How would that work? So for example, if we did n squared things, I think that would not do so well. For example, if we asked the minimum over the whole list, that wouldn't work. So we could do some sort of merge sort. That would be nice. If we can sort half the array and then the other half somehow. And I think that would be enough to reduce the penalty. The problem is like an n log n, like insertion sort or something, would not do well because it needs to take like at most 6 constant factor. Something's missing. Okay, this is good. Right. So how does this problem work? Did they make this in the right order? Okay. So for example, like the naive thing would just be to do this, and then we move the minimum over here, and then like we do this, and we move the minimum over here, and so on. I'm pretty sure that's too much. So for example, actually, how much is it? So it's 10 to the 8th plus it's 10 to the 8th divided by the length. So we do ceiling, so we add I minus 1 over I. And how much is that? Is it too much? Wait, is that it? Does that work? Oh, maybe it just works. Okay, I guess it just works. Cool. So I was wrong. Well, we are just supposed to do the insertion sort. Okay, well then that's the strategy. We simply query for the minimum of the whole range. Then now we know where the minimum is, so we move it over here. And then now we know that this is the global minimum. So the next smallest element must be within this range. So we query that, we move that over. Then now we know that's here, and then we query this, and etc. until the whole array is sorted. And in fact, we can avoid making the last query for one element because we don't even have to do that. We know it's just one element, so that's cool. Do I need to print in the case number? I need to look at this sample. Okay, so it says initially the judge will send you a single line consisting of two integers, t and n. So read in n there. Then yeah, okay. So for I equals 0 or 1, I is less than n, I plus plus, query m, I, n, and print line, then c into x. If x is not equal to I, then we do the swap. That should be it. Let's try, for example, 5, 3, 2, 4, 1. Or 5, no, that's like the worst possible case. 2, 4, 3, 5, 1, something like that. Okay, so 1, 5. Ask for the minimum, we'll give you 5. Ask for the minimum. Oh yeah, we swap 5 and 1. Okay, so ask for the minimum of 2 and 5. Now it's at position 5. So swap 5 and 2. Ask for the position 3. Make sure we don't do that. 4 and 5 should be 5. Cool. Looks like it works, yeah. I mean, it's like fairly simple. I'm surprised that works though. On larger n, I don't think it would pass because it's sort of like it's n log n. It's like harmonic series. It's the sum of it's like 10 to the 8th times the sum of n over I, which is n log n. Or actually, it's not n over I. It's 1 over I, which is 10 to the 8th times O of log n. So it's not the best, but okay. Anyway, I think that it should just work. So let's see. Matrygons. Matryoshka is a type of doll that originated in Russia. Their defining characteristic. Oh yeah, I do. Interesting. Okay, it's geometry. Sets of regular convex polygons that follow a similar nesting pattern. Okay, Matrogon consists of a set of regular convex polygons such that regular is like they're all the same size, right? Wait. Regular polygon is that equiangular, yeah, equilateral. Okay, cool. So it has to be a divisor, I think. Or no, not necessarily a divisor, but the GCD, wait. Oh no. Oh, this is a problem on coforces. Wait, isn't it? Wait, this is a problem on coforces. Calculate the largest number of polygons that can be part of a Matrygons such that the total total number of sides is exactly n. Oh. How does that work? Okay, interesting. Oh wait, no, it does have to be divisible. Yeah. Is the judge just slow? Okay, so yeah, this is how that works. So every time. Okay, no, it was a totally different problem from coforces. TLE. What did I mess up? Oh, is there some... Oh, shoot. Okay. Man, I forgot that this existed. That we have to... Yeah. I don't know why they do this, because this is never helpful, but... If x is equal to -1, x is 0. Okay, I forgot that existed. So if the list is sorted, it's 1, and yeah. Okay. That was dumb. Hey, whatever. I forgot that websites like to do that. Okay, so the idea is that basically when we have a when we have like, I'm not going to try and pronounce that anymore. When we have like a polygon of a certain number of sides, if we want to have some other polygon that's embedded inside it, then it has to be regular, and it has to be equiangular, which means that if we consider the vertex it starts on, then every other vertex it jumps to must be of the same distance, because it's regular and equiangular and inscribed in that circle, or inscribed in that other polygon. So what that means is, if we need a bunch of equal jumps, then essentially the new polygon's number of sides has to be a divisor, because otherwise it can't be equal all the time. So really we just need to check divisors, and I think we can pre-compute this with like dp or something. So I'm going to copy in my number theory and just do that. So we're going to pre-compute some stuff. Case number tc plus 1. And yeah. So essentially we just iterate over divisors. So dp 0 is equal to 0. Alright, now for... Actually, wait, what do we iterate divisors over? Actually, wait, I don't know if it's that simple. Maybe it's not that simple. So hopefully I do get this problem. With n equals 1,000 is simple. Also, all vertices are visible so far. Interesting. Wait, why did this not get, like, sample failed? Oh, that's annoying. Maybe there wasn't a sample. Oh yeah, so, like, test cases don't matter, we can pre-compute everything. Or wait, maybe we're not supposed to pre-compute it. So, like, for example, we could do DP on A, the last polygon, and B, the number of sides we currently have. And then that would store the maximum number of polygons, but still TLE. Okay, what am I doing? Oh my god. Seriously? It responds with... Wait, I didn't even see that part. It responds with 1 here too? Okay, I'm gonna like read through the whole statement very carefully, because this is just messing me up. It's an interactive problem. Yeah. Uppercase M, uppercase S. Judge responds with a single integer. Uppercase S. Why would it respond for that? What's the point of that? What would be the point of that? Uppercase S, swap operation. Swaps and responds with 1. Uppercase D, checks the list, responds with 1. Okay. I don't get it. Why do they have this pointless stuff? What is the point of doing this? Alright, well now I'm not going to check my place, because this is not going to be good. So I'm going to create a Matrygons with multiple regular polygons. So only option is these. Of course they use that word. They just want to flex their knowledge of polygons. Also, like, the answer is pretty small. The answer is at most log n, just because, like, it matters what, yeah, like, it matters, what we do. Swear to God, get another TLE. So, like, with the divisors, how is that solvable? So, for example, we could fix that we need to have a multiple of the previous one, or we can say we have to have a divisor of the previous one. There are questions here? Per test case. Okay, yeah, good. That would be dumb otherwise. I don't know how that would be possible. I guess that would be like a randomization thing or something, but still TLE? Is that like a thing? What is happening? What else am I messing up? After receiving the judge's response for the teeth case, your program must finish in order to not receive a time limit exceeded error. No, wait, maybe it's some like getting it wrong and maybe that's what it is. So it could be like a hit him wrong answer or something. I'm just very confused. What causes this? Am I like printing the wrong query or something? Oh wait, is it because I have to do I is less than J? Dude, this whole thing. I'm pretty sure that's it. The number of penalties I've gotten on this problem, I'm just like not doing what they want. That's so annoying. I definitely need to solve this fully, because I have so much penalty from this. Yeah, so now I guarantee I is less than J. Alright. Will this work? I guess we'll check that later. Given a fixed total number of sides n. Okay, I shouldn't get TLE anymore. Now I'm like actually doing the breaking if x is -1. Part of Matrygons, since the total number of sides among all polygons in it is exactly n. Yep. So, considering some number, how many like distinct things can we actually get? Imagine it can't be that many. Like for 100,000, for example. That's kind of a lot. Kind of. Finally. Okay, I can be done with that problem. Alright, good. Good. So now, how do we do this? Get the 2 polygons, yeah. For fixed n, we either take maybe we don't pre-compute stuff. Maybe we are supposed to like figure stuff out based on n. So for example, for fixed n, with 1 polygon we could take exactly that. Interesting. Why don't we use like powers of 3? For 33. Yeah, we could do something like that. So actually, we know what the smallest divisor is. Maybe it's like fixed. Maybe it's fixed. No, it can't be fixed. Oh wait, so if for example it's a multiple of 3, then if the total number of sides like mod 3 is how does that work? So if we take 3, then we're left with some other number. But now we know we're iterating only over divisors of 3, right? So does that help somehow? So for example, like we have 33, for example. So we take 3, and we're end up with 30. Or if we don't take 3, then we end up with the same number. Oh yeah, wait, does that just work? You can only take a number that's, no, it doesn't work that simply, but we can only take a number x where n mod x is equal to 0. Because otherwise, if n mod x is not equal to 0, every other polygon we take, we're assuming we're starting from the minimum and going upwards, every other polygon we take will also be a multiple of x, meaning that n mod x will never change by taking the other polygons. So the only polygons we're interested in are divisors of n. That's kind of interesting. So that reduces the transition space greatly. In fact, that might just be enough. Now we assume we do dp on we assume we do like dp on n and the last polygon. Now, like, I don't think this has many states. Yeah, the number of states this has is the sum for I equals 1 to n of d of I, where d of I is the number of divisors of I. Jesus, can't write it all. But, yeah, this is kind of cool because, like the last problem, this total cost is also n log n because it's equivalent, it's very close to the sum of from I equals 1 to n of n over I. Because instead of divisors, we'll instead assume we're counting multiples because it's the same thing. Which is O of n log n. So the number of states is small, and the number of transitions is also small because we're only taking multiples. Maybe. Well, is the number of transitions small? I feel like it isn't actually. Oh, right, no. Because again, we only consider divisors of n when we take that. So it's like n, it's like the sum. So really the complexity we're interested in is the sum of di squared. Because this will have that many states and it will have that many divisors as well. So, naively, I feel like that should be fine. Although I'm not sure. So, okay. Interesting. So, this isn't gonna be nice, is it? So if we consider like the map solution, how would this work? This is like a pain. 3 is that, okay. So 4 I equals 3. So I call my magic number theory template and I say get divs. Okay. Now 4. That's kind of messed up. So let's see, if I minus x wait, what do I need to do here? If y mod x equals 0, then dp of ix, no wait, best equals min best dp, so I minus x, and we ask for y. Best. So like, yeah. Okay, let's see how long this takes. So for now, I'm going to set it to 1,000. We can maybe optimize this later. So cn to n, so we take its divisors again, 4LX D, so then if it lands us in a spot like that, it's just a constant optimization. Ants equals max ants dp I. It's sort of messed up. It's like the next polygon we're going to take is this. It's not exactly the last polygon. X. So I guess we'll see. Okay. Right. The map pairs. Something still messed up. Why? No match for operator. Okay, I guess I can't do that. What? Pair long int. Oh wait, this should be X. What now? Oh my god. Come on. What do you mean I was not declared in this scope? Oh wait, no, that's right. Yeah. This should be N, N, and N. Good. Anything else? Yes, that is important. Okay. No, wait, that'll take a while. How long does it take for 10,000? Oh, it's messed up anyway, but... Okay, why is it messed up then? It should be max, that's why. Why is it still 1? Why would it still be 1? So, CI. So what happens here? Okay, so for 33, for some reason none of these other things exist. Come on, CI. 0 is fine. Okay. So for 33, we consider its divisors. Consider the divisors of those divisors. Why are we considering the divisors of the divisors? Oh wait, this should be X mod. Wait. No, this is the next thing we take. And I should mess with a bit of stuff. Yeah. Okay, I don't get why that makes it 1 though. So for example with 22, so here we should consider 9. Alright, am I just like wrong in my assumption? No, I'm right. Wait. Why does 30 not consider 6? Oh, it's the divisors of I minus x. Okay. Vector LLD. Okay. So di. There we go. So di. So this should be I minus x. There we go. So we don't need to check that anymore. Actually, that's a stupid condition anyway. That makes sense. No, it does not make sense. What? Doesn't make sense at all. Wait, how do we even get... Oh, what? What am I considering? Right. And it has to be greater than 3. And x is greater than equal to 3. Everything is related to 3. It's still 4. I don't know what's up with that. Why are we allowed to do that? Why am I just said and x is greater than or equal to 3. Oh, I see. So these parens should be here. Yeah, that messes things up, I guess. Good. Okay, this still has the opportunity to be wrong, so we should make sure all these conditions make sense. So we get that. So now, if this is a constant optimization, because if we end up with 2 or 1, it doesn't really matter. Like, we can't do anything with that anyway. So, and x is greater than or equal to 3. So, for y in the divisors of the previous number, if that is a multiple of this number, and that number is greater than this number, so it has to be not the same number, then set best to the maximum best and the DP state for that. Then we set the DP state for this. And here we simply consider all of it. So actually this can be 1 because it doesn't hurt that much. So actually let's just say n equals 5, just to test it. I just want to see how fast it is. Just take a few seconds. Okay, actually there's a pretty decent optimization I can do. I can make this instead dp of like a bunch of things on its own. And then this can simply be nx. That might be faster just because it doesn't have like such a big log. But maybe it actually won't be, I don't know. Actually no, it's only 1 log, so it should be definitely good. So I minus x. Yeah, I don't know why I wasn't doing that before. Maybe it makes it like simpler. 0 I. Okay. Should be faster now, because the log is like slightly less bad. Okay, bit faster. Test the big one. If it's under 40 seconds, we pass. Actually, if it's under 20 seconds. Huh. That kind of matters, doesn't it? There's a smaller limit for the smaller test case, so I might actually fail the smaller one and pass the larger one. That's actually possible. That could happen. Is that a thing that could happen? Could we fail the smaller one and pass the larger one? No, it won't. It'll short circuit. Damn. Alright, is there anything else I can do? And dpi minus x, now find y. This is to avoid creating keys that shouldn't exist, because that would also make the log larger. So if it is not equal to that, then this should be like star it. Okay. Oh wait, it should be like it to the second or something. The second value in the it. Because it's like a pair of key values, so we need the second value. That makes sense. Is this faster or slower? Hopefully it's faster. Because now we don't create the key y if it shouldn't exist. So the log should be a bit better. But maybe it isn't. Oh, it's the same amount of time. Okay. Well, hopefully Google servers are faster, because I mean it is Google. Nope, not what I meant to do. And then if that works, I'll submit that and try the next one, I guess. Is there anything else? Is there any obvious other optimizations I can do? I don't think there is. 3, 2, 1, it does get that right. Yeah, hopefully the servers at least aren't slower than my computer. Like I said, it is Google, so it should be good in that regard. This part doesn't matter at all. It's all the pre-computation. So maybe we change everything to int. Does that make it faster a bit? Because it is doing mods and stuff. Oh, actually, the worst problem is the map. Maybe it'll make a difference. Maybe it won't. I use this, by the way, to just make sure I don't like overflow accidentally. Because usually I make the assumption that LL is long. Is it any faster? Guess it wouldn't speed up the map that much. What makes it slower? Oh wait, I forgot to do the input. Okay, wait. That's dumb. I'll give it the input, see how long that takes. Yeah, okay, I thought it was slower, so I just wasted 30 seconds. Cool. Oh, it's much faster. Okay, submit that then, yeah. Because the answer can't be greater than n anyway, so we can use ints everywhere. Okay, that's much faster. Yeah, perfect. And like, so much else we need to do for that. 1 x equals 0 and y is greater than x. dp dot find. I trust it. Okay, good. Hidden pancakes. They love pancakes, don't they? We're cooking n pancakes in total. We cook 1 pancake with a 1 centimeter radius, 1 with a 2, 1 with a 3, 1 with an n. Okay, so it's like the pancakes one from last time. Do we cook each one? We lay it on top of the previous one. I see. So in increasing order. Just cook the pancake with radius 3. And cook the pancake with radius 1, lay it on top of the first one, and both are visible. Wait, what? Oh, not necessarily in that order. Okay. Lay on top of the previous made pancake with their centers coinciding. This way, a pancake is visible from the top of the stack when we first add it. Pancake only becomes hidden if we later cook another pancake with a larger radius. For example, say we cook 4, cook 3, awesome. Alright, got that. So, shouldn't be doing so terribly. Yeah, no, seems like people speedrun this. Doing some dumb stuff. Okay. The remainder dividing the result by the prime, 10 to the 9th plus 7. Cool. Okay, so the first subtask we can do bitmask DP, that's not that hard. So the second subtask, it is harder. modulo the prime, 10 to the 9th plus 7. Right. It's like we're asking for the number of permutations where like there's some equivalent way to like represent this. So we know the mod is this. So if we consider the permutation we already had, how much is like predetermined? So when we say something is going to kill exactly like, when we put a new pancake on, we know exactly how many pancakes it has to be larger than. So really we know its position in the new permutation, which is interesting. So what happens here? 1, 3, 2, and 2, 3, 1. I guess we're creating equivalence classes or something. So we know that like this can be anywhere. The first, it's like, and for example, in this case, the first element can be anywhere. The second element must be greater than the first. Then the third element must be between the first and the second. No, it must be. It just has to be less than the other one. Yeah, so 1, 3, 2 or 2, 3, 1. I see. So actually, we don't know its exact position in the permutation, I guess. We know it's... Rather, we have like a... I guess we're creating like a directed acyclic graph or something. So for example here, we have some relations between the elements. So for example, for the first sample, we know the first element can be anything. The second element has to be less than this. The third element is second. meaning that it's greater than, meaning that in this case it's less than this. No, wait, hang on. This doesn't make sense. I'll make these edges actually, yeah. So this element has to be, no wait, that does make sense. So this element has to be less than this. Then this new one has to be less than the larger one, but greater than that one. And then this element, because it eats everything else, this has to be greater than this and greater than this. And so for some other elements, for example, for like 3, 1, 1, and 2, so this can be on its own. This specifically has to be greater than that, and this specifically has to be greater than this. So the problem is we can't add these edges naively because n is up to 10 to the 5th, so that's not going to pass. But even if we could, what would we do about this? Permutations are hard. I never understand how to do problems like these with them. So I guess we'll find out today. Yeah, sample 3 is impossible. It's like if we have this, so basically it's a directed graph. And we're counting the oh wait, no, this is not greater than. This is less than. So if this were n squared, we have this directed graph, we're just basically counting the number of topological sorts on it. The problem is there can be a lot of edges, particularly when we have something like 1 and then 2 and then up to n, that's the input sequence, because that would create an edge for every possible value. So this would not work so well. Actually, no, that's sort of interesting. I think maybe it does work because when we have let's see, how does this work? So number of topological sorts should be something doable with like, actually wait, no, maybe it's not easy to do that. Is this something easy to do? Let's see, Quora. Is this like MP hard or something? Okay. Alright, so maybe this isn't like doable. Maybe there's something better in that the number of less than edges we have isn't that many. Or wait, the number of greater than edges we have isn't that many. Because when we have a greater than edge, that element is irrelevant now. Yeah, when we have a greater than edge, the element becomes irrelevant because it's just like gone. So so topological orderings, but on like a weird graph. Are there any? Wait, is it a tree? Oh yeah, it's a tree. Oh, it's a tree. Okay. Right. Yeah. Okay. Yeah. Yeah. Right. Yeah. 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 Okay. So basically, now that I've actually like grown a brain, here's how this problem works. Okay. So the first element can be anything. Now we consider the second element. Now, if it's going to be larger than the first element, then we add an edge between this and this, and we say this has to be larger. And otherwise, then this has to be less than it, but like it sort of doesn't matter. Actually, wait, no, it might matter. I feel like it maybe it does matter. I don't know. Um, does it matter? That is sort of important. Hmm. So maybe the problem is if we have all ones. Okay, now I still need to grow a brain, apparently. So how does one grow a brain without, I don't know, doing something? How does one grow a brain? Okay, that one's fun. Could solve a lot of these edges is the problem. Well, but they're also kind of like implicit less than edges. I guess. Kind of. So how does this graph work, for example? Well, these are the implications we have. So you can see that uniquely determines the elements. And here there are two. There are multiple orderings. We kind of do care about all the relations, though. Also, we kind of don't. Like, really, only having this is enough to figure out the whole thing. So, actually, wait, no. What is enough to figure out the whole thing? I think it's not that. Does everything matter? Ugh. So we consider like a graph where we direct edges. So directed edge means that this something is greater than the other thing. So for example, here, and then here, Oh, and then here. That does basically do it. Yeah, that tells us everything. That is enough. We don't really need the other edges. Oh wait, so all the edges point in the same direction, don't they? Do they? I don't know what I'm saying. What am I saying? No, I don't think I'm saying anything. This is the graph we have. So here, like, these two are sort of just together. We don't really care about those. They can be anything in relation to each other. In the third case also. So how does the third case work? So this has to be greater than this, and then this has to be right. So the other edge, what does this tell us? It's like we have a certain number of active elements. Then we need to know, we're given like the position of the new element in the set of active elements, but not in the set of inactive elements. I'm going to read the other one too. So R rows and C columns. Let's see. So they're all 10. F is 10 to the 6th, S is 10 to the 6th. Or up 10 to the 6th, not necessarily 10 to the 6th. So here, like, so only the costs are different, right? So of course we only swap two different elements. We only swap two different elements if it helps us. Because we can swap any two non-adjacent elements by doing two flips. This is only in the visible verdict. No. So can we represent this as a flow problem? So for example, if we say that doing the flip will cost us 10 to the 6th, there are a certain number of flips that we immediately have to do. So for example, sometimes if we have too many m's, for example, we need to flip some of those. If we have too many g's, we need to flip some of those. I'll assume m is 1 and g is 0. Then doing a swap is equivalent to like moving flow across. So it is like min cost flow. So doing a swap is equivalent to like moving flow across. Okay, interesting. So I'm gonna do this then. This is no, I don't need this. This is Ben Q's template just because I don't have min cost flow myself. I plan to learn that soon, probably because I like need to memorize some things, but not right now. So let's do this because this seems more approachable. Right. So basically, like when we have the same number of m's as when we have the same number of m's in one grid as the other, then we basically assume that when we do a flip later, we have to flip something else in return. So really, the only reason we would do a flip is to swap it with some other element, which would be like another flip, I think. Yeah, so the only reason we would do a flip here is so we can flip some other element later, because we have to do that anyway. So we might as well fix the element that we're going to flip now. And doing a swap is equivalent to sending a unit of flow across. Right? Is there any reason we would send a non-integer amount of flow? I don't think there would be. So yeah, basically we add an edge between every pair of elements, saying that we can swap those for the cost of 2 times f, or we can swap them adjacent ones for the cost of s. And yeah, so then we have some like extra flow. So it's actually similar to the problem I copied this from, which is like, it's actually kind of the same thing. Actually, yeah, it's very similar. The problem I was doing is landscaping from Musico, where basically you can swap, I'll explain this later. I'm just gonna submit this first, and then yeah. Okay, so string mat so 15.2. cn. So yeah, it's all 10, so it has to be like flow. Mat ij. Nope. This is just c into mat I. If mat I is equal to m plus cm. Actually, this is like the difference in m's, so we'll call it that. So this is mat 0i. This is mat 0i. And this is 1 and 1. So then this is, we subtract it now because the difference decreases. So now if we have more m's in the first grid, all n's is equal to, so it's the number of flips. I'm going to call it that. So we read in n, m, f, and s. F times absolute value of dm. Actually, wait, how does this work? I did some magic in like, I did some magic here before. Right, so yeah, if something is already equal, then we can sort of ignore it. There's no reason to, actually, wait, maybe there is? When would we do that? When would we not ignore it if it's already equal? Actually, yeah, that's not necessarily true in this case. Oh, wait, is it? We can have multiple edges. Yeah, if something's already like fixed, and the only reason we would make it unfixed is to like use it as like a medium to swap through it. But then eventually we have to change it back to being fixed anyway. So I think we can remedy that by doing some stuff. How did I do it here? I was smarter back then. So let's see what we need to do here. Oh, right, okay. Okay, so if we have more m's in the first grid, then we need to get rid of some. Okay, yeah, this was smart. Okay, so if mat ij, wait, this should be j as well. Zero ij is equal to m, and the other one is equal to g. And this basically says add an edge saying that we need to get rid of this m. M is 1, g is 0. So we need to get rid of this m. And to get rid of this m, we need to give 1 unit of flow to this, and then say that we need to get rid of it. So we add an edge from this to that. M times I plus j. Yeah, it's the row in the column, so it's the number of columns, number of things that, it's just like a position. So we add it from T is just like a temporary. So we add an edge from T. So T is like the source. Or like the starting vertex, n times m. And then T is the ending vertex. So we add a edge from the source to this vertex with, I think capacity is first. Yeah. So capacity 1 and cost 0, because that's the initial thing. Like we sort of get that for free. Else, this is G and this is M. MC dot add edge. Now we need to get something here. So this is from this to that, and then to the source vertex, because we need to get flow to here. Now we consider the other things we can do with this. We can swap these to directly. Okay, so for example, we can swap the two indirectly for a cost of 2 times f plus their distance. MC dot add edge. So it's 2 times f times their distance. Or no, wait, is it 2 times f? No, wait, so we can, yeah, so if they're different, we can like flip both of them. And that'll be fine. So it'll be 1, and then the cost is 2 times f, so we can flip both of them. We can swap like intermediate cells until we get to that one. And we assume that doesn't change anything else because if you wanted to do some other swap, then you could swap something like later and then not change it. Like the point is, if there was a way to swap it so that the swaps change the rest of the grid, then you can do it in a way that doesn't and still have a good answer. I think. So here's what I'm saying here. So we have like an F, and then we want to move it to this S, and we want to swap these two. Now I'm claiming that the rest of the sequence is all S's, so that the only thing, all S's are all F's, so that the only thing it changes is these two, since everything else will be unchanged. Since if not, say there's some F here, then we could do this swap and it'll be better, so we don't care about this swap. In fact, we can do this swap and then that swap, and then it would be better. I think. Might also just be easier to like maybe it's easier to just like not do that. Maybe we just don't make that assumption. I guess we don't really need to do that, do we? We just say like, if this is filled, we send it flow. If this is not filled, we send it flow. And then sometimes both of them get flow. Yeah. So then if this is equal to 1, what the edges I was going to add? So to do two things, yeah, we can do that. So if this is equal to 1, then we add the edge between them as well, saying we can swap them for s. Okay, and the final part is, this is the smart part. Where we say now we can add an edge from the source to this vertex, saying that we could give that flow for the cost of doing a flip. So like for example, this is G. Then to give this flow, we could do a flip to M, but then later we need to flip something else to G. So the cost is of 2 flips. And the reason we can sort of do that is because it, and then basically we give it infinite capacity because we can do that however many times we want. And the cost of this is 2 flips because later we need to do that. And the reason this works is because if we have extra flow in the grid, we'll assume we don't care where it is. We'll just assume later on we'll flip that to get rid of it. And so the reason it works here is if we have fewer M's, then we're going to start off with a negative total cost, meaning that we're going to have to do some of these to get the total flow in the network to be equal, and thus like we sort of get some of the like unflipping, some of the M's back to G's for free. And here in this case, we sort of already ignore some of the unflippings. Or for example, we already sort of ignore some of these G to M's, so we need to pay an extra cost to do that. Actually, this cost is just some of the M to G's that we have from the extra M's that we have. So this is 2 times F. And then cout ants plus mc dot calc st dot second. Yeah. Oh. Call it like source vertex. By the way, this can be anything, it's just infinity. Okay. See how this works. -3. Nice. Okay, so something's messed up there. How does this work? Gets that right. Alright, so that's going to be a weak sample. Awesome. So 2 and -3. So it's too low. So we have more M's here. How does this work though? So the max flow is 3. Why would the max flow be 3? It should not be 3. It should be... The max flow should be 6. So that's concerning. Why would the max flow be 3? Why is the cost negative? That makes even less sense. How would this cost be negative? How is it this negative? What am I doing wrong? Okay. Make this non-global, I guess. Is that like a problem? Does that cause issues? I guess it does. Okay. It doesn't make sense why it would be oh wait, because it's using like... Okay, I see. Yeah, this is resize, so we need to declare it every time. Okay, now somehow it's off, and the flow is very wrong. Why would the flow be wrong? So if I just did this... Oh wait, this should not be else. That's why. Yeah, there we go. And this will pass this sample, because I think this sample is useless. Okay, let's see. What else can we do with this? So if we made this 1 in 1000, so then essentially we can do everything as a flip. We never want to do an adjacent swap. So that should be 1, 2, 3, and 4. No, everything, no, 3. Cost should be 3, yeah. So in this case, flipping isn't that expensive, so we could do it for 6. I think that's the best option. If we hit an M here, so we flip that one, and we swap these two for a cost of 8. Wait, how do we do 6? Oh, wait. I need to make a case that's hard. So we can flip that. Yeah, now we swap these two. Good, okay. It's like, I mean, passes samples. Doesn't mean it's gonna pass everything, but I have faith in it. I don't know why having different costs would make it wrong. It's like almost it's like very similar to this, except this didn't pass this because the constraints were too large, but it'll pass this because the constraints are 10. One and then cost of 2 times F. This is iji jj1s. Yeah, so if they're adjacent, we can swap them. Just make sure we don't do anything stupid. So if if ii is equal to j, if ii is equal to I and jj is equal to jj, just like ignore it. So when we add that edge, we add these edges. Yep, so we can swap things for 2f, or we can do that for s. Makes sense. Hopefully it passes the hidden one. I don't see like how it would pass the visible one and fail the hidden one. So I guess if we pass the visible one, it should be fine. For this I can get the subtask, it's not too hard. Oh, that passed easily. Okay. For this I can get the subtask, it's not too hard. Yeah, people have AK'd. Okay, sure. Would expect that. Alright, so I'm not that good at math, which means that this is kind of going to be hard for me. Hidden pancakes. Yeah, alright, but that gives us this. So now we just need to figure out the last one. I mean, I can submit some dumb, like, bitmask DP. I can do that. But I also kind of want to, like, try for more. So, is this something I can do, is the question. So, it's probably a better way than representing it as, like, a graph. Or I'm trying to, like, generalize something that's very specific. I think, although I don't know how to represent this at all. So wait, maybe we do know its actual position in the permutation. Almost. Well, no, we don't. No, we don't. If we knew its position, actually, if we knew its position, it would be predetermined. The thing is, we don't know its position. The only thing we do know is something. We know something. Yeah, we know something. Like, the reason I'm not coding this now is because, like, it gives a penalty for... Actually, you know what? I don't care about penalty. I don't think penalty is my problem. I'll just write this now, and then we'll return to the hidden verdict after, just for, like, safety. So... Wait, actually, how does this work? Oh, that kind of... How do we even do bitmask DP, actually? We definitely can't enumerate all permutations. How do we do bitmask DP? N being 13 means that, like, 2 to the 26. It's kind of close. we need a thing for we need a thing for first the number of elements we use just in general, and second the elements that are active. I don't even know how to brute force. I could easily TLE. So then what? Actually, with this, we can use the topless art representation. So that would indeed be 2 to the n, but how? How do we do the harder version? It'd be nice to solve the harder version so that just like don't have to do the easier version, don't have to implement it. I mean, there's some other way to formulate it. Like for some value, we know its position in the set of active elements. Except when something reduces, or when the number of visible pancakes doesn't increase, then some of the pancakes get removed. And so that means that is this another question, or is this the same question? Yeah, it's the same one. So when some other value gets removed, totally lost right now. So once some other value gets removed, what happens? So actually we do get a tree like this. Interesting. We do get a tree like this. I sort of like dropped that idea, but we get a tree when we do this. And then just some of the other values have relations to each other. Specifically, if we consider the removal time of each element, two values are related to each other if what? How does that work? What am I even saying? I'm losing track of myself. Two values are related to each other if their removal times are what? Actually, each thing has an interval of time that it's alive for, I guess. And so if the two intervals intersect, then the two intervals strictly intersect with like a positive area. Then they'll have a relation between each other. And if two things have a relation between each other, then what? Do these relations themselves also form trees? I mean, I guess they would, right? Like every element has to be greater than every other element it has a relation with until it's removed. So do we get some like intervals? It's not exactly intervals. Well, how does this work? We get some like groups that have to be next to each other. Right? So how does that work? At every point, the number of alive elements is a decreasing sequence. I don't know how to do like combo problems. This is like my weakness. Man, I have a lot of weaknesses actually, but this is definitely one of them. Just like counting things. Just like learn some more tricks for that. But I guess one of the things we can try is, so we know at every point the sequence here is going to be decreasing. Like if we ordered them by their original indices, then the sequence will be decreasing. So when we stick on a new element, it's kind of like every element has a representative. What if we draw this in a different way? What if we draw this like this? Well, wait. How do we draw this? So this element is bigger than everything. Which means initially, like, here this is like this. Then, so we start off with this. Then here, we know that this is less, so this has to be here. Then here, this element is going to be greater than that one, but less than this. And so this relation we can sort of ignore. And then here is going to be greater than that one. So if we have some sequence like 1, 3, 2, no, that doesn't make any sense. Like 1, 2, 2, 2, 3, 1. Maybe that would help. So here, for example, we have this first one. Then here, this is less. Draw this very down. Then here, this is greater than that. But it's less than this. So it's kind of like a Cartesian tree. It's sort of interesting. Then here, this has an edge here, this has an edge here. This edge is implied, so we can kind of ignore it. So then with this 3, this has to be less, so this is sort of here. Then like the point is when we get this, we remove this edge. Yeah, we remove that edge. So that's sort of how that works. And this will eat up that one. So if we had like another 2 here, how would this work? So this 2 would be like, we just had this 3. So this 2 would be here. We basically are just making a Cartesian tree, right? So what? Let me do like a DP over this tree. What do we do with this? Right, then like the number of topless sorts on a directed tree is like n over like the product of degrees or something, or n factorial over the product of degrees. Right? Yeah, it is. Okay. I need specifically Cartesian trees. Why would this be here? Why don't they just like have their own Cartesian tree thing? Yeah, I'm just gonna do this. Okay, so that's kind of cool. For It's not degrees, it's size. And we break ties by saying this 2 will always be better than like any other 2, but it will not be better than any other 3, I think. Wait, how does that work? It will be better than any 2, but a later 2 will be better than it. Yeah, I think there's some sketchiness here, but I think it's resolved by the fact that we only care about the nearest adjacent larger element or smaller element. Also, this whole article is like so like the point is to do RMQ and O of N, which is like OP. Is it? Does it not? Is that not the build a Cartesian tree? I think like. I think it works this way. I don't know. I don't have a better solution, so I guess we'll see. This is minimum, yeah. So we want, yeah. Cool. Size. Yeah, so size v equals 1. V size v plus equals dfs x. And we need this. And I need modular inverse. Yep. I could pre-compute it, but it doesn't matter that much, so. Yeah. I don't know why I call it par. That should be a function. Okay. Copy pasting algorithms. Alright, what's up with that now? Yeah. E size V. I don't understand how that would happen. I have mod defined, right? Is MM messed up somehow? What? Ah, right. Right. That is why I have this warning. Because I expect that to work and it doesn't. Okay. That is wrong, but at least there's something. Why is this wrong? See I. Why did that have the parent of 2? Wait. What? That should be relevant, but I don't know why. This is the largest. Oh, wait. No, we do want minimum. So this whole thing is messed up. Okay. Right. Should work for this. Yeah, okay. So it's just messed up here because there's no answer here. Right? Okay, so how do we check for no answer? Well, so what are the parents here? 1, negative, and 1, and 1. So answer equals 1. It's only impossible if there's a gap of more than 1. Otherwise, it's always possible. So if I is greater than 0, and AI is greater than AI minus 1 plus 1, and it's equals 0. Nope. Guess that works. 1, 2, and 0, and this would pass that. Yeah. Okay, so this is copied. I trust it works. CP algorithms, they're usually trustworthy. This is that. So we check if the answer is 0. So yeah. And then we convert it to a tree. We do DFS on it. And we use the standard formula, or it's not standard, but it's a problem I've solved before, the number of topological orderings on a tree. Okay, if this works, this was kind of cool then. We sort of like, we reduce this complicated graph of relationships to just a tree. Let's see, 10 to the 5th. Yeah, just because it was messed up before, it doesn't hurt to do this, actually. Yeah, clearing it every time. We clear child, P is overwritten, parent is overwritten, size is overwritten. Cool, alright. I guess we'll see. I feel like this is also overcomplicated. Like, there should be some other way to... I don't know. There's probably some other way to do this. Okay, I guess it works. Never actually used a Cartesian tree before, though, so... Come on, show me my real place. Yeah, except I have full points, so it should be better. Alright, not the best, not the worst. I do hope... I expect my rank will go up a lot when people don't get the full scores, because these subtasks were really easy. Actually, maybe not this one. I don't know. Maybe, there might be some greedy solution involving this one, but this one, like, you could definitely like do the brute force and not really get the full solution. I don't know. I mean, maybe this is probably easier than I thought. I'm not that great at combinatorics of all the topics, so there's a decent chance I might have overcomplicated this, but it's still a cool idea otherwise. Okay, so I'm gonna go over solutions now because I don't have anything better to do. So for this one, minimum sort. I'm not going to read the problems. I'm kind of like slightly rushed because I have to do something at 1, so I'm just going to go over the the solutions themselves. So in this problem, basically we need to use some sorting algorithm, right? So the standard sorting algorithm would, for example, use comparisons. So in this case, we would do a comparison of, for example, like 2 values. For example, like bubble sort. It does a lot of comparisons. So we compare 2 values, and then if we find that this one is greater than this one, we swap them. And if not, we don't need to swap them. So bubble sort in this case would take n squared. So it would basically be n squared times 10 to the 8th over 2. Because the interval is 2, right? So it would certainly work, because asking the minimum of 2 elements is simply asking, like, which one of these 2 is smaller. And if this one is smaller, then it needs to be moved so this can be sorted. But there are also some other sorting algorithms that may work. For example, selection sort, where we find the minimum of the whole array. Say it's here. We move that minimum to here. And then now we know that the minimum element in the entire array is now here. So that means that some other elements, that means that the next smallest element is not going to be here, it's going to be in this range of the array. Meaning, we find the minimum in the whole array, then we get rid of that, and now we're solving a smaller problem. Now, that is what selection sort is, right? I think so. Wait, hang on. I need to make sure I'm talking about the right thing. I remember the sorts, but yeah, repeatedly find the minimum. Let's just divide into 2 parts. Yeah. Yeah, okay. Take the smallest element. Yeah. Right. So now we find the minimum again here. We move that over. We do it again. We find the minimum on this range. We move that over. We get that, etc. until the whole array is sorted. Now this is kind of convenient, right? Because we have an oracle that tells us the position of the minimum value on a range. That's the query we get, right? So like this can be done all in one query because the interactor tells us this. So what's the total cost for this? Well, the first query we do is 10 to the 8th over n because it's the whole array. The second query we do is 10 to the 8th over n minus 1 because it's everything but the first element. Because we need to exclude this because otherwise we would query n and like we would just like this is the minimum. We know it's the minimum already. It wouldn't give us any information. So then now we know this is the minimum, so we need to query this, and it's 10 to the 8th over n plus 2, n minus 2. All the way up to 10 to the 8th over 2 in this final case. Because there's no point querying this last one because like it's just a single element. Yeah, so now how much does this cost? Well, in general, it's the harmonic series, which is essentially 10 to the 8th times. The harmonic series is the sum from I equals 1 to n of 1 over I, which is exactly this if we just like consider going from 2 to n instead of from n to 2. And so it's sort of known that this is O of log of n, just because of like math magic. I have a blog that I always link that explains why, so I will do that. And here, in this case, so the fact that this is log n means that it should be sort of like, it should sort of hint that that's sort of close to the solution, because this is 6. 2 to the 6th is 64. In fact, e to the 6th is 403. So this isn't actually log, it's like ln, natural log. Right, so basically like computing it manually, so it should hint that it's sort of like nice to do. And computing it manually, it's really like at most 4 times 10 to the 8th, meaning that it'll pass for any n. So it's fine, we did it, we're good. So basically we just do selection sort, and we use the query to find the minimum efficiently. Yeah, so for this one, I don't really, actually wait, I'll go over the code for this too. Because why not? So, ignore this, this is something else. So, all these TLEs, by the way, were like misreading this part, the interactor. Note that for every operation, even like after a swap, it gives you a number. So you have to be careful with that. You have to read in the number every time. And you have to make sure it's valid every time. And note that it forces I to be less than j. So you have to be careful about that too. Would have been nice if they had a sample to like check that. Because most of these were just like my third mistake was just this. I was always making that mistake. So this is simply, we know n already. We read that at the beginning. And then for each test case, for each left index from 1 to n, we query the minimum on that. Then we find the minimum as a query. Then if this minimum is not the same position as we want to move it to by the selection sort, because if it is the same position, then it's sort of pointless and we waste the swap, and we can't do that anyway. So if this is not the same, we make the swap for the selection sort, and then we print done. And then we read in the number, and we don't make the dumb mistake of getting 3 TLEs, because whatever. Yeah. Okay. For this problem, Matrygons, the first thing to notice about the polygons is that, essentially, suppose we have some polygon like this. That should be 8 sides, so it's sort of ugly. Assume this is regular, even though it's very obviously not, right? So, if we consider some other polygon we're going to embed in this, because it also has to be regular, when we do a jump of length x among like the circle of vertices, so this is of length x, then every other jump we do also has to be length x because the polygon is regular. So we make some jumps of length x, and the number of jumps of length x we do is specifically pi, the number of vertices we have. So the total number of vertices we jump through is pi times x. And we need that to be equal to pi plus pi minus 1, the previous number of vertices. Meaning that pi is going to be of the form pi minus 1 over x. And so that means pi is always going to be a divisor of pi minus 1, is the basic idea. Another thing, it always means that if we assume we're taking the and the other thing we can observe is that there's also some divisor relationship between pi and n, because consider like the first polygon we take. So if p1 is not a divisor of n, that means that n mod p1 is not equal to 1, is not equal to 0 by definition. Also, we're considering smallest, so I'm sort of reversing the order they use. Actually, I'm reversing my own order here too. Basically, if the smallest polygon is not a divisor of n, then it means n mod the smallest polygon is not equal to 0. And every other polygon is going to be a multiple of p1. I mean that, for example, p2 mod p1 is equal to 0, and p3 mod p1, that's not a p, I don't know what that is. p3 mod p1 is also equal to 0 because they're all multiples of p1. That's like sort of definition. Meaning that the later polygons will not change the value of n mod p1. Meaning that if the smallest polygon is not initially a divisor of n, then like n will never become 0 because this quantity is always not 0. So there's always some remainder left over. So not only do the polygons have to be like multiples of each other, but n also has to be a multiple of the current polygon. And specifically for any n, like if we start with n and then we take polygon p1, and then the new n we end up with is n minus p1, and then we take the next polygon, this has to be a divisor of this, and this has to be a divisor of this as well by the same argument. And then n minus p1 minus p2 mod p3 is equal to 0, and etc. So for a given n, we don't really have that many choices, is the idea. And so for n equals 1000, basically a sort of... Oh, it's over. Okay, how long was that? Oh, I didn't get this? I guess it was wrong. Weird. Okay, I didn't know it was possible to get that but not get the other one. Okay. Guess I made a mistake somewhere. How did that happen? Ah. Jesus. Alright, that's... Oh my god. Okay. Just choking on one or two. It's not the first time I've done that either. Okay. Well, I guess I'll just like... I don't know, I'll just explain this. Cool. So, yeah, so basically this can inspire some solution like... For example, dynamic programming. For n equals 1000, we can do dp on like on n and the last polygon we used. And then we can pre-compute this because n is like just a number. So we can pre-compute this, and then that way that gets rid of the t factor. So in this case, it's just n times the number of last polygons we can have was equal to the number of divisors of n, and then that again because that's the number of transitions we have. So of n times d of n squared. I feel like I just like overcomplicated everything because other people found this a lot simpler. So anyway, it turns out that because most elements don't have that many divisors, like this even works for n equals 10 to the 6th. That solution. So yeah, in this case, that's just what I did. It's like kind of relatively close to the time limit, but it still works. So in this case, we that's basically what this represents. A is a map because we don't have infinite memory. So for this, dp of this is 0. Then here I use the template to just get divisors. So I get the divisors for this number. Then for each of these, where each divisor of this, we consider this being the last polygon. So we make sure the new range of polygons is not 1 or 2, because if it is, then it's impossible. Then now we're at the state nx. So we consider the other state n minus x and y, which is like where y is some multiple of x, because y is the next polygon we use, and n minus x mod y is equal to 0. So simply we iterate over the divisors of n minus x, and it must be a divisor of x, and it must be greater than x because we can't use the same polygon multiple times. And then so over this, we simply say dp of n and x is equal to max of y of dp of n minus x and y. Where y has some specific constraints, specifically the constraints in y are this. So those are the states we can transition from. And then that's our pre-computation, and then eventually we just do that. Yeah, okay. I don't know why I failed this. That's sort of weird. Yeah, anyway, I don't have that much time, so let's finish this off. In this one, basically we convert it to a lot of relations between elements. So for example, for 1, 2, 2, and 1, this one is sort of on its own. And this one says that because this is 2, this one must be less than this one. So a directed edge, so x being less than y, x to y means that x is greater than y. So in this case, we know this is greater than this. Then for this value, well, this has to be, we know that this is greater than this. And this sort of like has to kill one of the other pancakes. So it can't kill this one because then it would by default kill this one too. So instead, we just have it kill this one. And then also this one is greater than this. That's sort of another constraint on this. And then here, this element is no longer relevant because like we don't care what it is in relation to this because it's already dead. There's no strict constraint on it being not dead or dead by this element. But in this case, in this one has to be greater than this one, and it has to be greater than this one. So this gives us a a DAG, directed acyclic graph. And then a permutation is valid if it satisfies all these constraints. So really, it's just like a topological sort. So then the answer would be the number of topological sorts on this graph, which is fine. The problem is that's like impossible. It's not NP hard. It's like some sort of like complexity class that's like not doable. So it's not doable in polynomial time, which is a problem. And we have n squared edges anyway. So neither of these would work. But there is a way to count them over trees. And the way we would build a tree is simply that many of the relations we have kind of don't matter that much. So for example, let's consider this. Let's consider like a different way to draw this element. Like representation. So for example, we have this. This is the first element. Now the second element has to be less than this. So we have this sort of relationship. Then the third element has to be between these two. So we have this, and we have this. But then we might as well get rid of this edge, because it's sort of like dumb. There's no reason to have that edge, because it's sort of implied by this. And then this element has to be greater than everything else. It has to be greater than this, and it has to be greater than this. But again, we might as well not have this edge, because now it's sort of like useless. So really, we end up with a tree. If some element is larger than every other element, then we add an edge from that only to the largest element that hasn't been killed yet. Otherwise, if it's in between some other elements, then we sort of like, we can add an edge, for example, here. For example, say we had this. Actually, we could add this edge. Then if this was like in between some other elements. Actually, yeah, we would add this. If this was in between some other elements, we could add this here, because now this is greater, and we can add this to the element that it's greater than, and then we can remove this edge. So it ends up being equivalent to building a tree where like the it ends up being equivalent to building a tree where like every element, it's like its parent in the tree is like the largest element. Or it's not like it's like very similar to its nearest greater element, except it's like only on one side, kind of. Like if we consider the nearest greater element on the left side and on the right side, or on the left side and on the right side, we take the smaller one, we take the smallest of the nearest greater element. So we can do it that way, or we can notice that it's equivalent to this thing called a Cartesian tree, which is just like, it's just something that we can do. I'm not going to define this here, I'll link this article in the description as well, but that's basically what this is. It's just a Cartesian tree. So we build this Cartesian tree, and then we're interested in the number of topo sorts on this graph, or on this tree, or topological sorts. So for example, consider some tree here. And the trick is like, it's some combinatorics trick where we use this formula. So the number of permutations in general is n factorial. However, we have to exclude some certain permutations. Specifically, this value must be the largest. This value must be larger than everything else here. So in this case, draw another node. In this case, every permutation works except for the ones where this is not the largest element. So really that means that like for every permutation, this has 7 possible positions it can be in. But this has to be the larger one. And specifically, this element has to be before all of these. So the number of like relative, for each permutation, like we have to put this first, and then we can like sort of do these however we want to. So really that means that like there are the same number of permutations where every element is first. So like for example, there are x permutations where this is first, and there are x permutations where this is first, and there are x permutations where this is first. And that, and that, and that, and that. Every element can be first in the same number of ways. But we only care about the ones where this is first. Meaning that like the number of permutations that are invalid are like the number of permutations where everything else is first. And so that's equivalent to like dividing by the number of constraints we have with this element. So like of this group of 7 elements, this one has to be the largest, which means we divide by 7. And then of this group of 2 elements, this one has to be the largest. Which means for any permutation, only the ones where this one is larger than this one is valid. So it's sort of like the idea of like counting like strings where there are like identical letters. Like for example, how many different strings can you have by permuting this? And then the answer is like, it's like the multinomial theorem. It's like 9 factorial over 2 factorial, 2 factorial, 4 factorial, 1 factorial. You're basically like excluding certain things that are the same or they don't work. And in this case, you exclude some of the ones that don't work. The only ones that work are the ones where this one is before this one. And they're the same number here. They're the same number of these permutations as these. So only 1/2 of the permutations work. So here, this would be multiplied by 2. In this case, this doesn't have any relation, so it's sort of like multiplied by 1. Here, this is greater than 4 elements, so again, only 1/4 of the permutations work, since only 1/4 of the permutations have this as the largest one. So that's divided by 4. This one is 1, this one is 2, and this one is 1. So that's the answer. And essentially, once we have this Cartesian tree, then we just need to do a DFS to find subtree sizes, and then the answer is n factorial times the product of, or divided by the product of size I for all I. Yeah, that basically does that. I'll go over how I got the first subtask to retiling. I don't know how to, maybe I just made some mistake or something. Oh yeah, and in the code, I basically just copied the code from the link I found. And then this is just finding subtree sizes, then we divide by the subtree size, which is equivalent to multiplying by the inverse. And it's also impossible only if like we have some adjacent gap that's larger than 1, otherwise it's always possible. Because we can't have more than 1 visible pancake in a turn. We only put 1 pancake on. But in any other case, we can kill as many pancakes as we want using like a specialized pancake. Yeah. Yeah. Like we use a pancake that's specifically designed to kill only that amount of pancakes. So then we like find the trees in this code I copied, and yeah, then we convert it to an actual tree, and then take n factorial, and then we DFS to divide by these stuff, and then print the answer. Again, here I don't know what's wrong. I might have just made some mistake. That's most likely. Maybe the use code test cases were bad, and then my solution like never deserved to pass in the first place. I don't know, I thought I would pass this. I guess not. So the basic idea is to represent this as like a min-cost flow network. And that's the idea. So essentially, when we're going to assume that m equals 1 and that g equals 0. So essentially, doing a swap from like 1 to 0 is moving flow from one spot to another with cost s. I might have realized my mistake. Wait, oh, that could be a problem, couldn't it? Oh, I didn't mean to. Okay, that was stupid. Man, I think I just need to like increase the capacities. Sometimes we swap across multiple things. I think I just need to like. Yeah, these shouldn't be 1. These should be 1. These can be anything. This should be infinity. This should be infinity. I think that will work. Okay, that was dumb. I think that's my mistake. Yeah, so basically we have an edge from moving from 1 to 0 is an edge with cost. Yeah, that worked. Okay, damn it. All right, well, whatever. Doesn't matter. Still qualified. It's okay. Yeah. So essentially, this is an edge moving from 1 to 0 with cost s. And this should be capacity infinity because we can do this as many times as we want. But the mistake I just realized I made is that I made this capacity 1. And I think it works in the easy version where all costs are 1 because you don't really need to do it multiple times. But in the harder version, it does matter. So we need to consider doing this as many times as necessary. So it should be capacity infinity. So for every pair of adjacent cells, we add this. We add the edge that considers moving one flow across with cost s and capacity infinity. To do flips, when we flip something, like basically the idea is we have to have the same number of m's as the same number. We have to have the same number of m's in both of them. So suppose like the number of m's in 1 is less than the number of m's in 2, then we need to do m2 minus m1 flips of turning g's into m's. We need more m's. And if m1 is greater than m2, then we do m1 minus m2 flips of m to g. And in any other case, when we flip an m to g, for example, or we flip the other way, then we also need to do an accompanying flip from g to m because they must be the same. So now at this point, we also build the network where like, this is some source node, and this is some sink node. And for every node, if it's an m initially, then we get an edge with capacity 1 because we get some flow from this being an m, and then we have to do something with this flow. And then if in the second grid it's an m as well, then we add an edge from here to the sink with capacity 1, meaning that in the final state, this has to be an m, meaning there has to be flow here. And so basically the edges so it's sort of like a smart trick where essentially like in the case where m1 is less than m2, then this is actually going to be negative initially. And that's because we sort of like, here we consider all these costs being 2 times f, meaning that when we get a flip and we add some extra flow to the network, later we have to unflip it, but we don't really care which ones have extra. Because when the flow is satisfied, we'll have a certain number of extras, but we don't really care which. We can just flip whatever is extra back to g, and then get that with cost f. So we just assume we're spending 2 times f for every flip, which is a problem because this sometimes overcounts. So if m1 is less than m2, that means sometimes we don't flip back because we need the m to g's. So in that case, the initial cost is negative f times m1 minus m2, or m2 minus m1, meaning that the initial cost is negative, so we sort of save that much cost because we don't do these flips back. And if m1 is greater than m2, then we do fewer of these, meaning that we undercount the number of times we flip m to g. Actually, no. In the first case, yeah, we undercount the number of times we flip m to g, meaning that we need to have that extra amount. So in this case, we add that. And then source is that, sink is that. We add some edges. This is this type of edge. If in the first grid it's M, we give it some flow. If in the last grid it's M, it needs to get some flow to the source. And then we also add an edge to every node with capacity infinity and cost 2f. Also, these have cost 0 because, yeah, like it has to. We get those for free. Those are things we have to do. So we add an edge from here to here with cost 2f, representing we flip this node from G to M, and then later we flip some other node from M to G. But again, we don't care about which. We just need to satisfy the flow network. Then we add the adjacent cells. If two cells are adjacent, we flip them with cost S. And also, we can basically swap two nodes. Like, for example, say we have this one being 1 and this one being 0. We can swap these two by flipping this one and flipping this one for a cost of 2f. And again, swapping is the same as sending flow across, so it's basically this. I'm not actually sure if we need both of these. We might not. Actually, I don't think we need both of these. Let me submit that and then see. So we might not need both of these, but I'm pretty sure, like, it doesn't really matter. It doesn't really hurt to add these edges to consider that option, but I don't think we need both of them. So, yeah, and then that's our network. Here, then this is the final result. We calculate the flow, and, okay, yeah, we don't need both of them. So we can ignore this case, because actually, yeah, I don't think we can either, like, get rid of this one or get rid of the one I just got rid of. Swapping with cost, or like adding some flip in and then reversing that flip later is equivalent to swapping with flips. So really there's no reason to have both of them. Where did my mouse go? Okay, yeah. And then from here, we calculate the flow, and then we add in our factored, like our answer, and then we add in the flow we get, or the cost of the flow. Yeah, so min cost flow, cool. That was a really dumb bug. That was really, really dumb. And we could have gotten like a much better score without that bug existing. In fact, this would have been around my place. So it's like not the best either, but it's still pretty good. I'd be happy with it. Anyway, we do qualify, so cool. Yeah, I have to do a thing at 1, so I'll be gone now. Hope you could hear me. Yeah, bye.